In today's topic, we're going to talk about the probability experiment. What is a probability experiment? A probability experiment is an action or a trial through which specific results, which may be counts, measurements, or responses are obtained. The result of a single trial in a probability experiment is called the outcome of that experiment. So now that we define the outcome of an experiment, we are interested in having all of those possible outcomes. The set of all possible outcomes of a probability experiment is basically called a sample space. An event is a subset or sub-collection of the sample space. It may consist of one or more outcomes. For example, think about a very simple probability experiment, which is tossing a coin. When you toss a coin, you basically have two possible outcomes. It's either head or tail. So your sample space has only two outcomes. It might be the head or tail, not both of them at the same time. So you end up with a sample space including head or tail. Each one of these count as an event. So if I ask you to find the probability of head, you're going to say that, hey, it is 50%. 1 divided by 2, one event divided by 2 events is a half or 50%. Another simple experiment is rolling a 6-sided die. So if you roll a 6-sided die, what are the possible outcomes? When you roll a die, you might end up with 1 or 2 or 3 or 4 or 5 or 6. So you can basically count the number of possible outcomes. You can write down the sample space as a set including 1, 2, 3, 4, 5, and 6. One of them is what you're looking for, but in total, you have 6 possible outcomes. It might be 1 or 2 or 3 or 4 or 5 or 6. So in general, you're going to say that, hey, we have 6 possible outcomes. So if I ask you to find the probability of having 2, you're going to say that, hey, 2 divided by 6, but this 2 is just one possible outcome. So the probability of having 2 is 1 divided by 6. The probability of having 5 is going to be 1 divided by 6. So each one of these count as one event. That event, 1 divided by the number of possible outcomes. Very good. Now that we introduced the probability, we're saying that what is a random variable? A random variable that we denote by x represents a numerical value that is associated with each outcome of probability experiment. In this class, we're going to discuss 2 types of random variables. One of them is called discrete random variable, which is basically defined as a random variable is called discrete when it has a finite or countable number of possible outcomes. We can easily list those outcomes. For example, if you go back to previous page and look at this rolling a six-sided die, you have 1, 2, 3, 4, 5, and 6. So you can basically count, right? For example, suppose X represent the number of students in the class. You can basically list how many students you have in the class. You can count them. And the key word that you can see is highlighted here is the number of. So when you're reading a paper, listening to news, or working on your homework problems, the keyword, the number of, represents a discrete random variable. Another example for you. Let X represent the number of banks in San Jose, California. You can easily find how many banks are in San Jose. There are a lot of them, but still it is countable. So you can say that, hey, we have a discrete random variable. Other than discrete random variable, we have continuous random variable. A random variable is called continuous when it has an uncountable number of possible outcomes. It's represented by an interval on a number line. So give us an example. Of course, let X represent the speed of a rocket. Of course, you can assign a number to speed, but you cannot count it. It takes numbers on an interval. It has minimum value, it has maximum value, and it takes some values in between. Another example, let X represent the volume of an engine. Well, we have a numerical value associated to volume, but can you count it? Can you list it? Of course not. It's impossible to list that. Another example for you. Let X represents the area of a floor. Can we list the area? Of course not. But we know that the area has a minimum value and has a maximum value. It takes on values in between two numbers on an interval. So basically, these are examples of continuous random variables. For a discrete random variable, you have a keyword, the number of. Now that we introduced different types of variables, we are interested in finding the probability for each type of variable. Take a look. Each value of a discrete random variable can be assigned a probability. By listing each value of the random variable with its corresponding probability, you are forming a discrete probability distribution. To construct a discrete probability distribution, suppose X is a discrete random variable. Possible outcomes are X sub 1, X sub 2, X sub 3, X sub n. Then you're going to make a frequency distribution for the possible outcomes. You can find the sum of all frequencies. You can find the probability of each possible outcome by dividing its frequency by the sum of the frequencies. So it should ring a bell because you learned about relative frequency in previous chapter. So the probability is basically finding the relative frequency for a discrete random variable. So again, pay attention here. Probability distribution for a discrete random variable is basically the same as relative frequency. For relative frequency, you had a class frequency divided by the sample size, or f divided by n. Now, for each x value, in a discrete random variable, you have some frequencies, and then you're going to take that frequency and divide it by the sum of all frequencies. Let's take a look at one example to feel more comfortable about these steps. An industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a score from 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. A score of 3 indicated neither trait. The results are shown at the left. I moved the table to the right so we have enough space we can write. So take a look at your table here. So again, a psychologist ran this survey. You have 150 employees. 24 employees scored 1. 33 employees scored 2. 42 employees scored 3. 30 employees scored 4. 21 employees scored 5. So again, think about a large class with 150 students, and then you run this survey for your class. 24 students answered the question and they got score 1. Out of 150 students, 33 of them got score 2. Out of 150 students, 42 got score 3. Out of 150 students, 30 got score 4. You can think about it as a test. Out of 150 students, 21 of them got score 5. Now we are interested in forming the probability for each random value. So please note that X is a discrete random variable because you can list X values right here. X can be 1, X can be 2, X can be 3, X can be 4, and X can be 5. So this is the definition of this survey. X is a discrete random variable. Now, how do we calculate the probability distribution? Divide the frequency of each score by the total number of individuals in the study. How many people? 150 people. If you add all of these numbers together, it adds up to 150. 24 plus 33 plus 42 plus 30 plus 21 is 150. So let us begin. Probability of score 1 is the frequency of score 1, which is 24. And you're going to divide that by total frequencies, or the total number of people who participated in the study. If you do the division, it's equal to 0.16. It means that 16% of 150 employees got score 1. So remember that when we talked about relative frequency shows the amount relative to the rest of the entries or outcomes or data in your collection. So the probability of score 1 is 16%. What's the meaning of that? It means that if I randomly select a score, it's 16% associated to 1. Or if I randomly select one of these people, the probability that they got score 1 is 16%. So now that you have your frequency, you can basically associate these to the frequency that you have. Let us move on to the second probability. The probability of score 2 is 33, which is the frequency of score 2 divided by 150, which is basically total number of people in the study. You get 22%. It makes sense. The denominators are the same, but the numerator is increasing. So we expect to get a higher percentage. So again, what's the meaning of that? It means that if I randomly select one of these people, the probability that that person have scored 2 is 22%. Let's move on to next probability. Probability of score 3 is 42, which is the frequency of score 3, divided by 50, 150, which is the total number of employees or people participated in the study. If you do the division, get 0.28 or 28%. And again, compare these numbers. The denominators are all the same, but the numerators are increasing. So we expect to see higher percentage. So if I take a random employee and want to know what is the probability of 3, that is going to be 28%. Next probability is for score 4, which is 30 divided by 150 or 20%. Probability of 5 is 21 over 150 or 14%. So these are the probabilities for each one of these scores. If you add these together, add these probabilities together, it adds to 100% or 1. The question also says, hey, graph this, use a histogram. Okay, let us begin. For a histogram, we need a horizontal line, which indicates x values, starting from 1 to 2, then 3, 4, 5, are all listed on x-axis. On the vertical line, since the highest probability is 28%, I'm not going to go more than 30%. I'm going to scale it to 30%. So again, look for the highest probability in your calculation. The closest number to 28% is 30% or 0.30. I'm not going to go more than 30%. Now, the probability for 1 is 16%. So 1 has probability 16%. The bar that represents the frequency, or in this case, the relative frequency or the probability, note that we are using P of X, is equal to 16% or 0.16. That's why the bar stops at 16%. The probability for 2, as you can see, is 22%. So this bar is going to stay around 22% or 0.22. We can match this height to 22%. For 3, the probability is 28%. So we look at 3. 3 is the representative for this bar. The bar has height near 28%. So this is the third bar. The fourth bar is going to stop at 20%. 4 is the representative for the score here with probability 20%. And finally, the last one is for 5. The probability for 5 is 14%. And as you can see, the graph, the height of the graph match here. In this question, you have the number of people in each property, which is represented by X. The frequency is F. So take a look. One resident is associated to 1,007,669 properties. So what happened is the statistician, the team, collected the data. They went to different properties and asked, how many residents are living here? in 1,007,669 properties, it happens that there is only one resident. 901,4,820 property have two residents in them. 514,359 properties have three residents in them. 386,524 properties have four residents in them. 174,968 properties have five residents in them. 71,739 properties have six people living in them. 31,109 properties have seven people living in them. 10,215 properties have eight people living in them. And finally, they found that 12,735 properties have nine or more than nine people living in them. So this is the data that you have. Question says, compute n, which is the total number of properties in the table. What's the meaning of that? It means that if I add all of these numbers together, the sum is the total number of properties they asked and surveyed. It happens that if you add 1,914,820 and the rest of these numbers, it adds up to 3,124,138. So the team of statisticians collected data by going to 3 million properties. Now we want to build the probability or relative frequency for each one of these. What are we going to do? We're going to divide each one of these numbers by the total. So let me pull up my calculator and show you how to do the computation here to get an accurate value. Let me share the screen with you so you see what we have here. So we are basically dividing each relative frequency by the total. The relative frequency here is 1,007,669 divided by 3,124,138. If we do the division, we get 0.3225. And because of this 5, we're going to round this up, okay? 0.323. That's how you end up with this relative frequency or probability. We can continue this process. If you continue this process, you can find the next probability, which is 914,820 divided by 3,124,138, which gives you 0.293. So basically it says, hey, you have 29.3%. So that's how you find the probability for each one of these data. So what's the use of these data? When you have the relative frequency or the probability, you can basically graph and visualize and analyze the behavior of your data. Let's graph the histogram here. On the horizontal line, you're going to have your x values, which is the number of people. On the vertical line, you have the relative frequency. So remember that here you have 32.3%, 29.3%. You're finding the maximum value, and you're going to stop at the maximum value you're not gonna go up to 100% or 50% or more. Scale it to the point that it is more convenient. So as you can see, the very first relative frequency or the probability is 32.3%. So what is happening here? It means that the very first bar, which represents the relative frequency for 1, stops at this point. We expect the next bar to have a smaller height. So here at 2, you have 0.293 or 29.3%. The next one is 16.5%. So as you can see, the bar stops here. The fourth is 12.4%, which is this smaller bar. For 5, 6, and 7, and 8, and 9, you can basically graph these. But what is the behavior of this graph? Take a look. The majority of the data are located on the left-hand side, and the tail is on the right-hand side. So since you have a tail on the right-hand side, you can say that the graph is skewed to the right-hand side. The tail is on the right, so you're going to say that, hey, the shape is right skewed. So if I ask you to find the typical value, if somebody asks you, hey, now that you ran this survey out of 3 million property, what is the typical number of residents? And you're going to say that, hey, since the data is skewed to the right-hand side, to balance this object, it must be located around this point. So it means that you have either 2 or 3 people per household. That is the center or the mean or the balancing point of your data between 2 and 3. So now that we graph this, we visualize this, we analyze the behavior, we're interested in finding the probability. What is the chance that x is less than equals to 4? What's the meaning of that? What is the chance that you have either 4 residents or 3 residents or 2 residents or 1 residence? What is that probability? You're going to add 0.323, which is basically the relative frequency for x equals to 1. So when you say that x is less than equals to 4, you're basically looking at these numbers. X can be 4, x can be 3, x can be 2, x can be 1. So what is the probability that x is equal to 1? It is 0.323, or this bar here. You're looking at the area. Plus, what is the probability that x is equal to 2? It is 0.293, or basically this graph area here, plus 0.165, which is basically this relative frequency or probability that we calculated for the area on the histogram. Plus, finally, for 4, you have relative frequency 0.124 for basically the area on the histogram. If you add these numbers together, it's going to be 0.95, or the probability is 90.5%. That's the meaning of that. That's how we calculate the probability when x is less than or equal to 4. When you have x at most 4, another wording for it, what's the probability that x is at most 4? It means that x can be 4, x can be 3, x can be 2, or x can be 1. You need to add all of these probabilities together to find the probability of x being at most 4. Next probability. So again, we have our relative frequency, we have our histogram. Now we are interested in knowing what is the probability that x is more than 5, x is larger than 5. So what numbers are more than 5? 5 is not included. Be careful here. It's a common mistake for students that they include 5. When we say that x is more than 5, you're basically looking at 6, 7, 8, 9, and more. You're basically finding these areas and probabilities, adding them together. Take a look. The very first probability or area is related to 6. The second one is related to 7, which is 0.010. Then you have the probability for x equals to 8, which is 0.003. And finally, you have the probability for 9 or more, which is very small, but it counts here. You get 0.004. If you add these all together, the probability becomes 4%. So what's the meaning of that? It means that if I randomly select one of these properties and ask, hey, how many residents do you have? And if I'm looking at 6, 7, 8, or more than 9, it happens that I only have 4% chance. So that's how we calculate the probability for a discrete random variable. And finally, if I ask you to find the probability that x is bounded between 2 and 4 inclusive, it means that you are basically taking the probability for 2, add it to the probability for 3, then add it to the probability for 4. So you're basically taking these 3 numbers and add them all together. So 0.293 plus 0.165 plus 0.124. If you add them all together, it becomes 0.582 or 58.2%. Look at the graph. We can basically see the behavior of this graph. If I add these 3 probabilities or areas, they basically form more than 50% of the total area. So that makes sense. Here, the majority of properties are occupied by 2 or 3 or 4 people if we add them all together. And please note that if there was no equality here, you're basically finding the probability that x is bounded between 2 and 4, which is going to be probability that x is equal to 3. Let's be careful about these symbols.